This is a video for AQA Discrete Mathematics. It's Graphs and Networks, section 1.3, where we're looking at minimum spanning trees using Prim's algorithm. Well, we know that a spanning tree is part of a graph that connects all of the vertices but has no cycles. So it has no closed paths of any form. So if we've got a graph, then it's possible to find a spanning tree, and of course there may be more than one possible spanning tree for a particular graph. So for example, we could in this particular question form the spanning tree which goes from S down to R, and then R and C, from R to W, and finally join W to L. So there's one possible spanning tree. You'll notice there that we've got 5 nodes, and therefore our spanning tree must have 4 arcs. But of course there are more than one possible spanning tree. There's the one that we've already done, which has got a total weight of 43. An alternative to that would be this one, which has a total weight of 51. The obvious question then is, how can we find the smallest, or what's called the minimum spanning tree? With a network which is nice and small like this one, then it might be possible to find every single possible spanning tree, and therefore just hunt through our list to find the smallest of those. However, in practice, for a larger network, and a network which is representing a real world situation, that's not going to be possible. It's going to be very impractical to do that. There'll be so many different possibilities that it would take too long, certainly on paper, and difficult to program for a computer to do. However, there are ways of solving this, and one of these was developed by a Czech mathematician and then later rediscovered by Robert Prim, hence its name, Prim's algorithm. And Prim's algorithm works as follows. It says, first of all, choose any vertex and connect it to its nearest vertex. So we could, for example, here start off by choosing the vertex, let's say S, and connecting it to its nearest neighbour, which is R, by the 11. So then connect the nearest vertex that is not connected to this solution. So we have to look what is nearest both to S and to R. So if we look at S first of all, we've got 12 and 22, and to R we've got a choice of 12 or 15. So one of the 12. So let's take the 12 going from S to C. And then we keep on going, so it then says repeat step 2. In other words, look at all of our points we've got now. So we've got S, C and R. And what's the nearest to any of those? The nearest one is L, coming in here with 7. And then finally we need to connect in W by coming from L to W. So there is our solution using Prim's algorithm starting at S. Well, we could ask the question, what happens if we started somewhere else? For example, let's this time start at W. We can see that going from W, then we would first of all connect to L by the 5, then to C by the 7, and now our smallest one is the 8, but that would get us back to W, so that's not part of our solution. We need to connect a new point in. So we've got a choice now of 12s. We can either go to S or we could come to R. So let's this time come down to R, and then finally we have the 11 connecting into S. So you can see then we get a slightly different solution to the one we had before. That's because we had a choice of the 12s, and therefore it's giving us a different minimum spanning tree. So you must be aware that minimum spanning trees are not unique. There may be more than one, but because of the minimum part of that title, they must all have the same weight, and these all have a weight equal to 35. Well, here's a typical sort of exam question, so a slightly bigger one. You would normally be asked to start at a particular node and work through using Prim's algorithm. So let us do that. This time we'll do it starting at A. So we start at A, and usually what we do is to list the arcs in the order that they're added. So we're going to go from A, and so the first arc we're going to add is from A to C, which is length 30. And we might indicate that on our diagram. We might use our diagram by just colouring in along that route there. And then once we've got to C, we've got to look at A and C. Well, from A it's 31, but there's a smaller route coming from C, which is 22. So we're then going from C to D, 22. If we now look again all the way around, remember, but the smallest one you'll see is from D to E, which is 18. And then from the network then, again, remember to look at every single point. So we've got 24 is our smallest. So that 24 comes from D to B. Again, looking all the way around, we'll see this time that our smallest one is 26, this time from E. So from E to G, 26. From G to F would be 21. So that's the smallest one. And then we've got one more to go. We need to connect H in, and the smallest route to connect H in is from G to H. So having produced our minimum spanning tree on the diagram, we could also say that the weight of the minimum spanning tree is just the total of all these different weights of arcs. So the weight of the minimum spanning tree is equal to, in this particular case, 174. So make sure that you understand the algorithm and how it works, just to go over then one or two different things that might go wrong, or what mistakes are often made in trying to apply the algorithm. The first one is really just a silly one, not reading what a question asks you to do in terms of which node to start at. It's quite easy if you don't look around and check carefully that you don't always add the shortest arc. Also, if you don't keep track of your spanning tree as you go by highlighting a diagram or drawing the spanning tree, it is quite easy to form a cycle by accident. You must remember that you look at all of the vertices when you're looking for the next edge. So look at all of those that are already on the tree and join them to the next nearest one. Always remember to record the order of the arcs as you go along. It's silly to do it once and then have to go back and do it all again to work out which order you used. Show sufficient working. That's usually to write down the order of the arcs, and maybe if you're asked to draw the actual minimum spanning tree. And then don't forget to state the length or weight of the minimum spanning tree itself. Right, that was Prim's algorithm then. That's the end of this video. We'll look in the next video at the same algorithm, but this time working from a table rather than from the network itself.